Yes, please.
So good day, everyone. Today, Pratik will be talking about quantum channels and how to correct the error in the quantum channels. What he started delivering the lecture last week. Today, he will continue from there. Pratik, over to you.
Yeah, thank you. So I'll just first start briefly review what I told last day. So we saw that given a channel lambda, we can construct its environment assisted. So let's say lambda is represented in its Krauss form like this. Then from there we can go to its environment assisted correction that I can write like this. Where phi k are CPTP maps. So that is the basic notion of how we correct a channel through the assistance of environment. So last day I discussed that one important result, which was that for any sorry, for any qubit channel, its corrected one-shot capacity, so corrected capacity of lambda is always log 2. And we also show that for any channel, the correct, so for any other channel, its corrected classical capacity, single shot, is always greater, is lower bounded by log 2. So now, and this was actually shown by some connection with local state discrimination. We use the famous result of Hardy and Walgate to derive this conclusion. So today we will start with another important result, which is also a connection with LOCC state discrimination. And this was by John Wattus. Let me just get the reference first. Yeah. So the reference is this. The main relevant, so this paper was regarding something, and we will use only a corollary of this result. And the main motivation of this result which we are using is to identify certain channels which has always suboptimal corrected capacity. So identify quantum channels having so first let me define what we mean by optimal. So let me formally frame what we mean by optimal, a channel having optimal corrected capacity. Optimality condition is that, let's say I have been given a channel lambda which maps from CD to CD prime. Now optimal means this corrected capacity single shot of lambda should be log D. Now this means the following two conditions will hold. First, that
It should be
there
log. It should be log minimum of d prime. No?
Yeah, minimum of d prime. So I'm taking the input dimension d. So for that I'm defining this uh,
Yeah,
corrected
that's what I'm
capacity.
saying. Let's say your input dimension is C3 and
Yes.
output dimension is C2.
Yeah. I agree. Yeah, exactly. So that should be, yeah. So if a channel has this optimal classical corrected capacity, then I will say that okay, following two conditions will hold. One is that there exists a environment space, let's call it E, uh, and an isometry embedding links V, and V is a isometry from S to R tensor E. So S is the sender Hilbert space, R is the receiving Hilbert space, and E is the environment Hilbert space. And this holds this. And in the joint Hilbert space of the receiving and the environment space, so there exists an orthonormal basis set, let's say called psi I D, which is a subset of um, is such that V
Capital
psi
D.
I,
Capital D. I runs from 1 to capital D.
here, this is one to cap. No, this is the input Hilbert space. So this orthonormal basis is in input in sending Hilbert space. So that's why I'm taking this is a d-dimensional Hilbert space, no?
I see, I see.
That's why. And the output Hilbert space is also V acting on psi I belongs to R tensor E, and this set of states is perfectly distinguishable by LOCC. So when we are saying that this is perfectly distinguishable by LOCC, then we are actually allowing something more than what I discussed last day. So initially I said that okay, there is this isometry and this is the sending Hilbert space, sender Hilbert space sending some rho, and then there is this R and E. And when I talked about the environment assisted capacity, I said that the environment you are making some measurement, and that measurement outcome you are sending to receiver, and based on that output, based on the received measurement outcome, this receiver is applying some phi k. Now,
Pratik,
when I'm
Pratik,
saying yes,
I'm getting a little bit confused. Let's say again 3 to 2.
yes,
Then you know that maximum 2 symbol Bob can decode,
yes,
even taking assistance from entanglement, whatever the thing is.
right.
So then ONB, even if it is 3 are there, that does that mean 3 I can decode?
No, 3k you cannot decode. It will depend on the I mean the output Hilbert space. If it is two-dimensional, then you can at most decode one bit of information.
Means 2 symbol we can decode.
Two symbol I can decode. Yeah.
So that's why
Oh,
there
I
exists
see.
a ONB of capital D, no?
Yeah. Right. Yeah, because that much I can only decode. Yes. So last day we said that environment is only communicating classical information to receiver, but now we are allowing something more, that also receiver can communicate back to environment and environment can again communicate back. So both way classical communication we are allowing, and even by doing that kind of LOCC protocol, if the receiver can identify the index I, from this V psi I, then we'll have this log capital D amount of information. So this is what I mean by optimal environment assisted capacity. So now in that paper, they have proved an important theorem, which I'm taking as lemma here. And the lemma is that you consider a maximally entangled state phi plus, which is of this form. And it belongs to some CD tensor CD Hilbert space. Now, you consider the subspace Q. Q is defined as the space which is the support of this. Means the orthogonal subspace of the maximally entangled state of CD tensor CD. And then they have proved this result that in Q, there does not exist any orthonormal basis which can be discriminated, which can be locally distinguished by LOCC. Even under two-way communication. And this holds only for D greater equals 3. So for example, if I take C2 Hilbert space, if I had taken C2 Hilbert space, so then my state was phi plus and the orthogonal subspace was spanned by, so the Q was spanned by phi minus and 0 and 1. Now in this Hilbert space, I can actually distinguish, there exists certain orthonormal basis which I can distinguish perfectly, but so that's the reason why I'm taking the dimensional restriction D to be greater than equals 3. And now using this fact, they are going to construct a channel for which they are showing that this channel has a suboptimal capacity. So for that, take the construction like this. So you take the sending Hilbert space S to be of D square minus 1. This D is of this D. And the receiving and the environment Hilbert space of CD. Okay. And now you choose any basis, any orthonormal basis from Q of this R tensor E Hilbert space. So let's take this ONB to be of this form. And you define an unitary isometry like this. So what does this isometry does? It takes an state from S, and okay, so I is the basis set of S. So it takes any state from this S Hilbert space and it projects this Hilbert space to this CD to this subspace Q. And since and so this defining this isometry actually gives us the channel, because I have defined the channel like this. So channel action you can recover by this trace this condition. This condition, it gives you the channel action, and for this channel which admits this isometric extension, now any let's say I take the input Hilbert space like say input states like psi I, and this psi I will be projected into the Q space due to this isometry action. So now the receiver and the environment will share some V psi I, and which is in this Q Hilbert Q subspace. And since in this Q subspace, there does not exist any orthonormal basis which can be discriminated perfectly. So this channel does not have any log2 capital D corrected capacity. So lambda constructed from this, the C corrected of lambda is always less than log2 capital D. So this was the example which was presented by John Watrous in this result, in this paper. So now I am going to discuss another important result regarding this connection between LOCC discrimination and environment assisted capacity, and that is by Lin-Chen. Okay, so Lin-Chen, they have, yeah, what is it? So the reference is, okay, I cannot find the reference right now, but I'm writing the DOI actually. Okay, so in this paper, they have shown an important result, and they have shown that you consider a bipartite Hilbert space of C3 tensor CD. And from this bipartite Hilbert space, you take any three-dimensional subspace. And they have showed that for in C3 tensor C3, any three-dimensional subspace, there always exists as orthonormal basis, which can always be distinguished perfectly. By LOCC. So this means that if I take my input, so now what the implication of this in this channel environment assisted capacity is that for all channel with environment dimension 3, the corrected capacity of those channels are at least log 3, because again you can send a state through this again you can send a state through this isometry. So you can send 3 symbols, let's say psi1, psi2 and psi3, which are mutually orthogonal, and you can have an in 3 entangled state. With environment I am taking C3, and it can mean anything, and this state,
Pratik,
yes,
hello.
yes,
So why is it necessary for environment to be C3? Means even receiver can be C3,
yes,
no?
yes, environment or receiver,
Means,
and yeah, either of them can be C3. Then also this
okay.
proof holds. Yeah,
Yeah.
actually I made the mistake. So if environment or the receiver have this dimension 3, then they can actually distinguish the I index, the massive, and so at least they can have log 3 amount of
Pratik, I
information.
have one
Yes.
confusion here. So
Yeah.
I think you have written that there exists a ONB which can always be distinguished perfectly by LOCC, right?
Right.
There exists a ONB in C3 space. So that ONB is chi1, chi2, chi3. Okay.
Yes.
And that chi1, chi2, chi3 are distinguishable, but chi1 prime, chi2 prime, and chi3 prime are not distinguishable.
Wait, 1 second. 1 second. I have to just check. Check. I think it is. Oh, okay, just let me check. I think I have missed something.
No, Mirda, what was your question? But
My question is, it is saying that there exists a ONB which can always be distinguished perfectly.
yeah,
Okay. Now, if that happens, now if suppose that basis is chi1, chi2, chi3, okay, which is distinguished perfectly, and this isometric extension making this psi1 to chi1, psi2 to chi2, and psi3 to chi3, then it's okay, fine. It would be log3. But there might exist some another basis which is chi1 prime, chi2 prime, and chi3 prime, which is not perfectly distinguishable, and you choose a different system.
No, that's what. So what you have to do is you have to choose your encoding such that
Exactly.
it maps to chi1, chi2, chi3, right?
Now this is my questions. Is it in our hand that how environment will make those transformations?
But capacity.
No, but
No. You know the channel, so no, you know the isometry.
Yes,
Yeah.
so that's what I'm asking. I'm a little bit confused.
So you can calculate. You can calculate which 3 states are going to chi1, chi2, chi3.
Right.
So is that always possible, right?
Yeah.
For a channel, it is always possible.
Can I say?
Yeah.
Mir, you think in this way. So you take QB depolarizing channel, a rephasing channel, rephasing across Z direction.
Yes.
But you encode in plus x minus x. What will be your capacity? Classical capacity? 0?
0, yes.
So capacity means you have to optimize over the encoding, no?
Yeah, that's true. But what I'm asking,
no, that's what I'm saying. So it says you know the channel means you know in that subspace there exists a orthogonal state, 3 orthogonal state that can be LOCC distinguished. Now this due to isometry, this orthogonal state will come from 3 orthogonal encoding state.
Okay.
So you use that in 3 encoding state for your encoding.
Yes.
That's all.
Here, that's right. I'm a little bit confused about this part that when, I'm not so sure about these things that can I manage that transformation?
Isometry is orthogonal preserving, no, always.
Inner product preserving.
That is okay.
I'm saying let's take this in this C3 tensor C3, this 3-dimensional subspace you have. Let's take this set of states are locally distinguishable, and this belongs to this 3-dimensional subspace.
I am saying, Pratik, I am just saying this. Just 1 second. Mirda.
Yes.
You just do one thing. You apply V inverse on chi1, chi2, chi3. Exactly. This is the solution.
Yeah. So you
take use that
I think there is one thing I think what I have to clarify means given a channel, can we specify the isometry? That is actually the mere question.
Yes.
Is there a one-to-one correspondence between a channel and isometry? I think it is not true.
It is not true, yes.
But in this case, we have access to the isometry, means we know the isometry. Then I think everything is fine. But Mir is asking whether there is a one-to-one correspondence between exact channel and an isometry. I think it is not true.
It is not true, but if you change the environment part, then your isometry would change. Actually, isometry only depends on the environment. So now, this is my question that, okay, you want to go a transformation from psi I to chi I, then actually, can you change your environment and create one isometry which will make this transformation psi I to chi I, not psi I to chi I prime.
Yeah, means I think in this kind of thing.
Yes.
Yes.
That isometry is not unique, but that is up to local unitary, no?
Three local unitary. So,
Yes.
so any local unitary of chi1, chi2, chi3 is also distinguishable
Yeah,
Okay.
exactly.
Okay,
if
now
it is in that subspace.
there is a point. Like point means, so then this chi1, chi2, chi3, and this chi1 prime, chi2 prime, and chi3 prime has to be connected by a local unitary from one side.
One side.
Yes, unilaterally. Yeah.
Yes. 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 True.
Then it is perfectly done. But here, suppose this chi1, chi2, chi3 is a non-orthogonal. Sorry, non-maximal, and chi1 prime, chi2 prime, chi3 prime are maximally entangled. I mean, I'm saying, suppose in some cases it might happen that they are not connected by a single unitary. I don't know. There is some ambiguity. I mean, that part I'm
No, but-
somehow missing.
But I'm saying that let's say you have given a channel lambda. Now for this channel, we know that, so what is the condition is that this channel has an environment dimension 3. Okay, so this environment dimension, if you know that this is environment dimension 3, then you actually know the isometry for this channel.
This
I mean-
isometry is under. There is equivalent class under under the environment.
Yes, with unitary equivalence.
Unitary equivalence also you can
Yes.
say, yes.
Means that unitary equivalence is there on the environment side.
Environment.
Only in the
Yes.
environment, yes.
And
Yes.
if
With a
these
single
states
unitary.
are distinguishable, then a local unitary equivalent is also a LOCC distinguishable. So there is no problem. Yeah,
Exactly.
Yes. Yes.
Got it. Okay. Now fine. Yes.
Okay. Now, and if in addition we have this receiving dimension also C3, then we will have this. So if receiver dimension is also 3, then actually we get the perfect capacity.
So, but Pratik, like I still have some confusion. What Mirza was asking. So, like, doesn't it matter? Like, aren't you assuming that the environment knows that among this isometric freedom, which one is there? That information also the environment knows. That is assumed, right?
Yes.
Yeah, I think it is actually
That has
assumed.
Means
Has to.
yes, the environment but can actually
Because we cannot know which one is chi1, chi2, chi3 or chi1 prime, chi2 prime, chi3 prime. Means if we do not know, then in which basis we will make the LOCC discrimination.
Exactly.
yes. So actually, this environment also knows the input state that are being sent. In that sense, they
But
can.
I think this kind
navigate.
of thing is always assumed, because even the original result, LOCC2 always you can get for any channel. For there also you need to know this.
Yes.
To apply Walgate Hardy, you should know which two states to distinguish, right? So I think these
correct.
things are always
Yeah,
assumed.
means without
Yes.
knowing the isometry, we cannot implement the LOCC operation, right?
Yeah.
Exactly.
Yeah.
Exactly.
Okay.
Okay. So just like any qubit channel has this corrected capacity LOCC2, then again from this result we get that for any Q3 channel, means C3 to C3 channel, it has corrected capacity LOCC3. Okay. So till now we have discussed only this classical capacity. So now I will go to a little bit about quantum capacity. So we again revisit the original paper by Warner and Gregory, which is this quantum lost and found that I referred earlier previous day. And there is an important theorem which they are saying that, let's say I have this lambda which is given by lambda rho, which is given by ak rho ak dagger, and this class corrected version is this. Now they are saying that this lambda corrected is identity, means you have perfect quantum capacity. This will only hold if and only if the lambda channel is a mixed unitary channel. So before going to further moving on, I'll just take some time to discuss mixed unitary and unital so that we are on same footing. So any channel, let's say I have a lambda channel which maps from CD to CD, CD in to CD out. Now I will call this channel unital if so in identity on d-dimensional Hilbert space gets mapped to identity of d-dimensional output Hilbert space. If this property holds, then I will call this channel to be unital. And I will call a channel to be mixed unitary if it can be represented like this. Let's say I have lambda rho, and if I can represent this channel like this, then I will call such channels to be mixed unitary channels. So you can see these mixed unitary channels always have.
Pratik,
Yes,
in this
yes.
unital case, in this unital case, you have to just mention that map is a positive map also.
Unital, yes, yes.
Not positive, means CP, CP.
Yes.
Unital has a two conditions. One is I by D to I by T, and it is CP.
Yes, but I'm only talking about the channel part only. I'm not making I'm not talking about most general linear maps. So that's why I assume. So yeah, that is true. Any channel has to be CP.
Pratik, I have a doubt little bit.
Yes.
So unital channel physically it means it's the spontaneous process.
Yes.
So that means entropy will cannot
Decrease.
Let's say now input channel is C3, input dimension is C3.
Yes.
So now what is my I by 3? So the entropy is log 3, no?
Log 3. Yes.
And output dimension is 2.
Yes. Log 2 then.
So will it be then spontaneous process?
This unital, when people define unital, dimensions they make the dimensions equal.
Yeah, that I used to know. Means are you?
Yeah, me also. I think.
But
Pratik,
yeah, but I think this unital definition is generally this, and this entropy decreasing part only holds if these two input Hilbert space and output Hilbert space are same.
Oh, that is
Under
the spontaneous transformation. Unital is
Yes.
mathematical. I understand.
Yes,
Fine,
yes.
fine.
So for mixed unitary channel, the Krauses are of this form. And if we go into the classical analog of this channel, so in classical version, any channels. So in classical case, the analog thing of channel is stochastic map. Stochastic map. And analog thing of unital is bistochastic map. And that of any unitary, sorry, unitary is reversible map. So mixed unitary is nothing but convex mixing of these reversible maps, which are called random reversible maps or RARE maps. Now in classical dynamics theory, classical dynamics, it is an important result by Birkhoff and von Neumann. Birkhoff von Neumann theorem, which says that any bistochastic map is nothing but a convex mixture of reversible maps. So set of bistochastic maps is same as RARE maps. And that is called the Birkhoff von Neumann theorem. Now what happens in quantum case? So in quantum case, if you take map from CD to C2 to C2 means qubit maps if you take. Then you can show that the set of unital, so any unital channel, you can write it in this fashion, like this. So basically unital, all unital channels are mixed unitary. But for CD D greater than equals 3, this is no longer the case. And in fact, one can show that all mixed unitary channels are unital, but the converse is not true. So the set of unital channels forms a superset of the mixed unitary channels. Like this. So these are mixed unitary and these are unitals. So I'll come back to this Birkhoff theorem because it has some implications from this environment assisted capacity also. So this was just a side note for introducing this mixed unitary and unital things. Now Gregorothy and Warner, as I mentioned earlier, that Gregorothy and Warner showed this important result that if you have a channel and if you can correct this channel with environmental assistance to perfect channel, let's say identity channel or a unitary channel, then the only possibility is that this channel should be a mixed unitary channel. So this is an if and only if condition, and the proof is very nice. So one way proof is very trivial. Let's say if my channel is mixed unitary, so then I can always have a correction map so that I can make it an identity channel. So let's say I have lambda rho, which is given by the sum root over pk, sum pk uk rho uk dagger. Then my lambda corrected will be this phi k. Phi k will be nothing but 1 by pk. Sorry. So phi k will be nothing but this uk dagger, means like this. So phi k basically is an unitary correction. So that means that if my channel is mixed unitary, I can always make the lambda corrected to be identity. And the inverse proof is also very interesting. And for that,
Can I ask something?
yeah.
So let's say your lambda, the way you choose it, it's a convex mixture of unitaries. Let's say you have something like this, you have convex mixture of these unitaries, and this is multiplied with another unitaries. Okay, that is, let's say, V. I mean, it doesn't depend on UK. Okay, this is some independent unitaries. So now the lambda corrected will be proportional to this V.
Yes, exactly.
Okay.
Means then also you will have perfect quantum capacity, but it is not identity, but
Right.
it's some unitary transformation of the input state. The output will be.
Right. Okay, the criteria you has to have we have to have this convex mixture of unitaries, right? This is the criteria.
Yes. So if you take
And
mixed, yes.
yeah, another question in this line. Let's say you have a general map in the sense, let's say it's not actually the convex mixture, but it's something else. But is it possible to estimate your channel with some corrections? Let's say with this is the corrected channel will be close to this one. Like you cannot estimate completely. Like for this case, as you say, it's if and only if conditions. But
Yes.
if you have some error, then is it possible to predict your corrected channel?
Means I discussed last day that this correction channel that you are taking, it will make your it will determine your lambda correction. So this phi k channel that we are making now. So after you have to optimize over all possible Krauss decomposition and all possible this correction channel phi k, and that will give you some lambda corrected. Now what you can do is take this diamond norm of this lambda corrected and this identity. And this diamond norm you can express in terms of this phi k and the Krauss decomposition of this lambda. And then you can try to minimize and get the conditions on phi k and the Krauss, I think. I mean, yeah.
I understand your point. Like, do you know, is there any analytical result on it? Like,
No, I don't know.
okay.
But maybe one can check in the literature.
Okay, thank you.
Hey, Pratik.
Yes.
So I don't get the correction point. So if mixed unitary is applied there,
Yes.
then how do you know in which run which unitary has acted?
Oh, because this mixed unitary, if this is done, then this, so you know the Krauss. So Krauss are nothing but this PK UK of the actual channel. So now let's say let the environment make the measurement and determine the K value, and K value is returned to the receiving end, and then he will apply this phi K, and phi K is nothing but this UK dagger. I mean, the Krauss is UK dagger actually.
Got it.
Yeah, so I was going to prove the next step, that if my lambda corrected is identity, then it implies my lambda is mixed unitary. So this lambda corrected is identity means that I have this thing. Right? Means for any input state, whatever I give, my corrected after the corrected action of the corrected channel will reproduce my row as it is, and it should hold for any row. So this means that so there is an important theorem by I think Carlton Caves, which or someone, I forgot the name. So one second. Yeah. So there is an important theorem which states that no information without perturbation. So according to this theorem, if this holds, then I can always write this thing: phi k, ak row, ak dagger is nothing but proportional to rho with some constant pk, and pk is a probability, so pk is always greater equals 0, and summation over k pk is identity. So this part I actually don't understand completely, but if you assume this theorem to hold true, then from this condition you can actually go to here.
Pratik.
Yes.
Pratik, I think in the above line, when you're writing this summation over k phi k, I think individually all those phi k, ak row, ak dagger has to be proportional to rho, right? Lambda correction identity means individual all phi k, ak row, ak dagger has to be proportional to rho. Each and every run he will correct, right? So obviously summation would be that one, but this one, yes.
Yes.
If lambda corrections means identity, then phi k, ak row, ak dagger has to be proportional to rho.
Yes, that is the claim. But while they were proving, they have referred to this theorem, and they say that this conclusion you can draw using this theorem. So I don't understand this theorem there, but yeah, intuitively it also feels like that, na? And this should be the case. This should be the case. That feels like.
I got it. Okay, thank you.
So now let's say I want to derive. So now let's say take the trace of phi. So phi k is already a CPTP map, So if I take phi k trace of this, it is not, which is actually pk. And then, so actually if I take trace over this part, this will become pk. Actually pk is nothing but this. And since phi k is a CPTP map, you can also write like this. Because this comes from the CPTP-ness, means TP-ness of the phi k.
Can you, I didn't understand this point. Can you clarify?
Sorry, you want me to clarify this?
The last step, like how
Yeah,
it,
yeah,
let's say,
okay, I should have gone the other way. So pk, I can write this thing because row is trace trace of row is identity. Yeah. So from this equation, I can write like this. This is just using this identity.
yes.
Now phi k is a CPTP map, means let's say TP map is that lambda is said to be TP if this thing. This is a TP condition.
Mhm.
So since phi k is a CPTP map, we can always write like this. So phi k is acting on this state, so I can replace the trace of this as well here. Is it okay?
Uh,
I mean, you
no.
consider this part as x.
Yeah, this will give us state, right? Some row prime, let's say.
Some operator. It need not to be a state because AK are not
Yeah, right.
maps.
Yes.
Some
positive
operator, any operator. For any operator, this x is any operator.
Yes, then you have phi k and x, right?
Yes.
This.
So phi k acting on x, and since phi k is trace preserving, so
Right.
phi k acting on x, if this trace will be nothing but the trace of x.
Oh, okay, I understand. Okay. The trace will not change of this. Okay, of this x.
Yes.
Yeah.
Yes, that is the trace preserving condition. Okay, so now so this is actually pk, and this can only happen if, I mean, so this I can write like this also. And this holds for all row. So what I can write is this AK dagger AK is equals PK times identity. Okay. And for finite dimensional Hilbert space, this also always means that AK is nothing but an unitary. So this actually proves that my lambda channel is nothing but a mixed unitary channel, because this is the Krauss of the lambda channel. Okay, is it okay? Is it clear to everybody? Okay. So this was the proof of this theorem by Gregoretti and Warner. Now I want to go to another important result in this direction, and that was one by Warner. I forgot the reference. Okay, I'll refer it later. So Warner in 2005 has shown an important thing. So there in that paper, he has actually derived the not the single shot, but the regularized quantum capacity, corrected quantum capacity of a channel. And That one is you can find like this. So quantum capacity corrected of any channel in the regularized sense is given by, so let's say you are given a channel lambda, and you take the entropy of the input state S rho, and also you take the entropy of lambda rho, and of these you maximize uh, you take the minimum of the two quantities, and then you maximize over all possible rho. So this actually gives you the corrected quantum capacity of the lambda channel. And see, even for quantum capacity for any general channel, we don't have a closed letter formula, but the environment assisted corrected capacity, we have a beautiful closed letter formula due to Winter. Oh, sorry, I have made a mistake. This is not Warner, it is Winter. So we have a we have a closed letter formula for this channel. Now take unital channel. So first of all, this quantum capacity is for regularized versions. Means you take lambda channel and you take infinite copies of it, and so you take the lambda tensor n, and you find the capacity in the limit of find the capacity of this channel n times, and then you normalize it, and in the limit n tends to infinity. And here he showed that even if your lambda channel is unital, let's take lambda to be an unital channel, then what happens? Then the maximum yes,
Pratik,
yes,
so this Winter's result, so
yes,
it is for any arbitrary channel lambda.
yes.
Now, can you give some intuitions that why should it be connected to the entropy of the, in this way? Like, why should it be the entropy of the input channel and the input state and the output state? Like,
Mm, so that I don't actually know properly right now. No,
is it uh, is it connected to like how I don't know. Yeah, so that was I mean,
no, actually I understand your point, but yeah, I have not gone through the proof actually, but yeah.
no, I'm not asking for the proof. Okay.
No,
Okay,
but
we
I
can.
actually I
Yes,
also don't know the answer.
Yeah. Okay.
So if you take a unital channel and if you take the rho to be identity by D, so that is actually your maximum so if you take rho to be D, then lambda rho is also proportional to identity by D. And the minimum, actually, if you take both input and the output of the same dimension, so S rho and S lambda rho are same. And rho is for the rho equals identity actually maximizes the state. And so in that case, your quantum corrected capacity is actually perfect, means log D for D-dimensional systems. So from here, Warner and later by other co-authors like Verstedt and Smolin, they made a conjecture. So initially what Warner proved is that if you have perfect quantum capacity, then your channel must be mixed unitary. Now, in the asymptotic case, they are finding that even unital channel have perfect quantum capacity. And so they conjectured that, so their conjecture was that if you take unital channels and you take these unital channels, let's say lambda unital you take, and you take arbitrary copies of that, and in the limit n tends to infinity, it actually becomes a mixed unitary channel. So that was so in the sense, like in asymptotic limit, the Birkhoff theorem again come back. So so for a single copy level, unital and mixed unitary may not be same, just like as I draw this diagram. So for single copy level, unital channel is not mixed unitary, But if you take infinite copies or asymptotically large copies of this unital channel, then you can approximate that unital channel as a mixed unitary channel. And that's the reason what they have suspected, that is the reason for why they are giving perfect quantum capacity for unital channels as well. But and there were other results by Mendel and Wolf, who where they have shown that if you take so in that paper they have given an example of a unital channel, and if you take only 2 copies of that unital channel, that actually becomes a mixed unitary channel. So it was long thought that in the asymptotic case, in the asymptotic sense, this Birkhoff's theorem will again be re-established. But later in a paper, I'll just mention the result. Just yeah. So in this paper by Hagerup and Musat, CMP paper, they showed that actually no, even in the asymptotic sense, mixed unitary or unital channels cannot be represented approximated by a mixed unitary channel. Means, so their proof was like that. So for this unital channel, so this is the set of unital channel, and there is this strict subset mixed unitary channel. Then there also exists another class of channel which is in between them, and which they are called a noisy channel. So the conjecture was that if you take a channel from here under tensoring in arbitrary copy, this actually will come down in the mixed unitary domain. But they have showed the existence of certain noisy channels which are not mixed unitary, and even if you take tensoring of this, they actually don't come within this mixed unitary domain. So existence of such channel which are noisy, they are in general unital channel but not mixed unitary channel. So they don't reduce to a mixed unitary channel, and so the general statement, general conjecture made by Winter and others, that actually was falsified in that paper, in this paper.
By the way, what is the definition here, like of the noisy channel?
Yeah, so noisy channel. Okay, just a second. Um,
But this is like this noisy channel is like the fixed point for this channel is the identity channel, right? The identity,
Yeah.
right?
yeah, means all these. So noisy is a subset of unital channel, so it always preserves identity.
It's some kind of restricted noisy channel,
Yeah,
right? Like
yeah.
noisy is, yes.
So this noisy is not like the noisy means it is some kind of noise is coming. They are defining it noisy, but I think I forgot the definition. But like some fixed input, fixed dimensional ancilla you take and then you trace it out. I think Mirza, you remember the definition you were
Yeah.
discussing once?
Yes. So actually, this is in the Steinspring dilation. In that part, you can, in general, in case of a unital, you can take any environment systems and any unitary so that identity would remain identity. But in case of a noisy, your environment has to be mixed states.
Completely mixed status. Completely mixed status.
Completely mixed states. Sorry. Yeah, completely mixed state. Okay. Only that much restriction. Okay.
Yes. So this noisy channel, these kind of channels are strictly outside the mixed unitary channels, but they're all unital channel. The definition what meet the same. And in this paper, they showed the existence of some. So their paper was mostly motivated from a mathematical point of view. So they defined something other mathematical properties of this noisy channel, and using those mathematical properties, they showed that if you take tensoring of this kind of channel, some particular kind of noisy channel, they will never be come inside the mixed unitary channel. And so in that way, they actually falsified this conjecture. So that was all that I wanted to discuss today about this
I am
environmental.
sorry, like, I mean, why this conjecture is important? Like,
Because
I mean, in the sense,
so just I mentioned earlier that in classical system, any any unital or doubly stochastic channel, if you consider that, you can always write as a convex mixture of reversible channel. Now, if we go to the quantum case, then the idea was like that, okay, in quantum case also all unital channels should be mixed unitary channel. But it was shown that for CD d greater than 3 onwards, this is no longer the case. So unitals are superset of mixed unitary channel.
I mean, Pratik, can I just add few words on
Yes.
Tanmay question?
Yes.
So Tanmay, you see, in general, when you are actually re-establishing a channel, how to simulate that channel? One of the things is that in case of a mixed unitary, it is quite applicable. Like, okay, you just take some random number and randomly you are picking up some unitaries, and that's the way you are mixing. Okay, but in the simulation of a unilateral channel, which is not a mixed unitary, it could be a little bit difficult, right? You have to take some another ancilla, and then you have to apply some global unitary. In this case, global unitary is important, but in case of a mixed unitary, the global unitary is not that much important in the simulations process. So that's why people, in case of a classical, actually these both are exactly same. In the simulations process, any bistochastic split you can simulate by permutations and probability mixture. But in quantum case, if these two sets are equal, even in the asymptotic limit, then the simulation of a unital channel would be quite, I mean, practically doable, right? But since these two are not equal, so still there is some complication in the simulations things. So in that could be one of the importance from some physical perspective.
yeah, another questions I have, like, it's kind of.
And I want to just add one more thing regarding what Mirda said. And if you take the unital channel, so you can construct this channel to, so unital channel one, if you fix the input and the output dimension to be same, then you can show that, let's say I have a state which is rho and I act a lambda unital over it. So I'll be able to go to some state sigma. Now, this kind of state transformation under unital channel can be described by certain entropy monotone, which Manikda was referring to earlier. So the condition was like that the entropy of sigma should be always greater equals entropy of rho. And if you, instead of taking unital channel, if you take lambda mixed unitary channel, you are also given the same condition. I mean, for state transformation level, the conditions, the restriction, let's say whether given a state rho and I want to go to sigma, whether I can go from rho to sigma or not, that condition is essentially governed by these kind of entropic relations. And these two conditions are exactly same for unital and mixed unitary channel. Even though mixed unitary channel is a subset of unital channel, then unital being a superset of mixed unitary channel, let's say there is some channel lambda u which is on this side, which is not mixed unitary, and from using this mixed unitary channel, let's say I can go from rho to sigma. Then this theorem, yes.
Pratik, this statement, what you are saying, depending on this unitary, depending on this entropy, it is true in the asymptotic limit. I mean, rho. I mean, but in the finite limit, you have to be more precise. Like majorization conditions is the governing criteria for state transformations.
Like all the alphas, right? Like S alphas. Like it's, you have to check for
S alpha. So all Rayleigh or Sally's entropy. Yeah. So you can just add Sally's entropy. Both Sally's entropy, I mean, both unitary and mixed unitary conditions, Sally's entropy are the governing rule, and for both of them, governing rule is still same. That's point Pratik wanted to point out, but still they are not same. As a state,
in the finite copy, they're not same. You're saying? Hello.
No, I'm saying in the finite copy, the state transformation rule for both of them is same. Okay. Even in the asymptotic copy also, that is same, and that is same with only von Neumann entropy. But their structure-wise, still the distinction is there that unital is a bigger set and mixed unital is a smaller. That
Yes.
you wanted to point out, right?
Yes.
Yeah.
So maybe one could. So what is the reason why these two state transformation criteria are same? So one might think that in the asymptotic limit, these unital maybe are mixed unitary, but that is not the case. That I wanted to just add.
Yeah, so another questions I have, like
Any,
oh,
okay,
okay.
maybe the last
Sorry.
question you can ask, or otherwise, Pratik, if you want, we can continue the discussion next week also.
No, I am finished. I mean, this is complete.
Oh, okay.
If someone,
Maybe one more.
some other people can ask the questions. Manik has some questions.
Yeah, Pratik,
Yes,
can you go to where you just this unitary correction quantum where you just started?
unitary correction of this mixed unitary. You are
It
saying?
means quantum things where just you started.
Okay. Yes, this part.
Yes. So now mixed unitary, this mixed unitary lambda, yeah, mixed unitary, okay. Because you were there earlier.
This part you were saying?
Yeah, that one, that keep this line. PK, UK, ROK, UK dagger.
Yes.
Let's say I have applied, physically I have applied 10,000 unitary,
Okay.
different unitary. I mean qubit, let's say. And their convex mixture I have taken. So this is a truly physical process.
Yes.
So now environment dimension, should I take 10,000?
No, environment dimension, I think.
4 is sufficient environment.
Yeah,
Four,
because
four
yeah.
is sufficient, I agree. That means 4 Pauli I can apply. But physically I have applied 10,000, no?
Yes.
That system doesn't somehow, once the channel is applied, it doesn't bother whether I have physically applied 10,000 or somebody you have applied 4. Correction will be only 4 is sufficient, no?
Yes.
Yeah.
So
And so that kind of thing happen at state level also. No? If I tell you,
that is precisely my question. That state level, what we know, is it similar thing at channel level? It's at least here this is happening. That is precisely my question.
So
means like if I take convex mixture of all pure qubit states, I get I by 2. But I can get I by 2 just by 0, 0 and 1, 1.
Exactly. But I'm not talking about that. I'm saying I'm talking about a channel level. A channel, let's say 10,000 unitary mixing of unitary giving me a lambda channel. But from Krauss theorem, we know, okay, 4 Krauss is sufficient since it is C2C2 channel, C2 to C2 channel.
right.
So, but physical implementation are different, no?
Yeah, maybe physical implementation is different, but in the
but at
in the state level, suppose you have the convex mixture of some state, you are getting for some mixed state, and you have a spectral decomposition of that state.
Yes.
But both of them do not give you any difference in the statistics here.
That's why correction.
Operationally, they are same.
Yes.
That's why correction is not sensitive to that which physical comparison.
I mean the physically
Exactly.
whatever.
That's why it's not. That's why in the environment also 4 correction only will be there, even if you are having 10,000 unitaries. Ultimately, only 4 correction will be there.
Because this 4 correction is sufficient to correct whatever noise you have done by arbitrary number of channel implementation. I mean, so if you have implemented 10,000 unitary also, the amount of noise that has been incorporated, that can be actually, that is not that much that cannot be recovered by 4.
Yeah,
so 4 is sufficient to recover.
I'm trying to get a physical picture. That means, okay, using this 10,000 unitary also, what information leaked to environments.
Yes.
By 4 also leaking same amount information is leaked to environment. That's why from environment same process is giving back me the identity. This is happening.
Yes.
Yeah.
In physical picture, no? Am I right?
Yes.
So rather, there is nothing you can do. Even if you have the full power of environment and this together, like environment and system together in your lab, there is nothing you can do to distinguish whether those 10,000 unitaries were applied or 4 unitaries were applied. There is no thing you can do to distinguish that. Isn't it?
No, that this, yeah, fine. That is fine. I'm saying just another quick means clarity. So this unitary, mixed unitary, it can be according to one or what is the other guy? That their result, it is perfectly correctable. So similar result in classical, in classical picture should hold, no?
Classical picture means this.
I have some classical noisy channel. I am trying to make it
Oh.
corrected. But now my question is there any study whether is it only for double stochastics or for any channel, any classical channel, the correction will be perfect?
But Mike, the
I
classical
think,
channel, you have to first define the notion of isometry and all these things. That is there a way to consistently define isometry and all these things?
But I think it is
Classical.
always, by definition, it would be always true, because okay, the point is here you so all the information is going to environment. Okay, that's why we are calling it environment, and environment and systems is connected by classical communications, and that is actually full access. In classical world, that is the full access.
Yes, actually, in
Here
correlation
also-
level, correlation
Exactly.
is classical only.
Exactly. So that's why full access. So that means for any channel, not only W stochastics, rather for any stochastic channel also, it would be 100% correctable if you access the classical communications.
Yeah, I can see that. And my question is there a precise formulation of that?
Oh, that I don't
That
know.
No, so no, Pratik, Mirza, see, the problem is if I have a, first of all, let's say I have a classical channel, then can I write down the isometric evolution and all these things in the completely classical picture? Like I have to define all these things, no isometry.
this time
Like,
speed
can I think of
dilation
a can I think of yeah, exactly? Can I Stein
That
spin
would not
direction,
be
does it hold
classical.
in classical theory?
Yes.
Yeah, I think that
would
is
not be-
possible. Actually, once I
For
and
example,
Ananda
you
was trying, I think this Stein-Spring dilation you can define. in the
Just
classical
applying a global permutations and consider a pure ancilla 100
Yeah,
probability you can take and a
but
global
global permutation, if you do, then the final state will always be product. It will never be entangled.
correlated.
Because
you say?
entanglement you will not get in classical theory, no?
You say
Yeah, but
correlation.
you get correlated as we said.
It would be correlated.
No,
Classic-
how it will be correlated? It is global unitary. It should take pure state to pure state.
Why
It will
you
not
need
be
to-
correlated.
You are talking about classical things, right?
Yeah, so pure state should go to pure state.
You said probability.
No, I think what Sahil is trying to say is that if you input a pure state and after the isometric evolution, I mean, the probability vector
the
has only
global
one.
state should
But the ancilla you can take as a mixed state, right? The ancilla you can take as a mixed state, means the environment.
no, but that we don't do here, no? In this
No. means
quantum.
yeah.
No, what was the
In
question?
quantum thing, we can do it with a ancilla which is pure state, but we can define it also in terms of a mixed state.
Yeah, but in Stein-Spring dilation, I mean, even if you don't refer to the mixed this environmental state, you can still represent in the isometry form, na? But
Exactly.
in the classical, if I also think like in an isometry exists without referring to the environment state, then the probability factor of the input state has only one entry 1 and others are 0 in the probability factor. Now isometry will make it one entry, I mean, the output state of the isometry should also be like that only. So in that case, how will you define classical correlation? I think that is what Sahil is trying to say.
Exactly.
No, that's why I'm saying why you are thinking isometry, unitary, that is not a good language. You try to think reversible is the way, because permutation. No, that's why I'm saying permutation also not good things, because permutation, I'm saying, you see, I am giving a 2-dimensional coin to 3-dimensional coin. Stochastics math. All
Yes.
you can think for permutation, but I can think as a reversible. That is a natural. That permutation.
Maida, just give me 1 minute. Just so when you're saying a system is, so what is happening in a channel, a system is going to output as well as environment. Okay, we are saying that, right? So in that case, what we'll do, the most basic things we can do, okay, we take a system that is a probability vector P, we take an environment that is another vector probability vector Q.
That we don't want to take, because we are talking about isometry, not unitary.
I'll come to that point. I'll come to that point immediately. So I have a probability P, I have a probability Q for the environment. On top of that, both of them together, I will put a permutations.
Yeah.
I'll apply global permutations, and that is the most general things.
Good.
And then I would just trace out this, I'll trace out this environment part, and that would be the isometry for classical case. I'm saying that one.
No, but there is one more thing you should add here. You should say that I will take the environment state to be heads and then start.
Exactly.
Because that is what you do in quantum.
Pure states.
So let's say it is a coin in head state. That is how you should start. And then you are saying system can be in any state, environment is in head state, and there is a permutation on both of them.
Exactly.
Yeah, but that will not give you correlation between environment and system.
Yeah.
Why not?
Because that will how it will give. It will give only head will first head will can go to tail, second head can go to tail or identity or the swap. Nothing else.
If you take the pure one, then you cannot build any correlation, at least in the classical case. Yeah, that is true. That is true. Because quantum theory provides you some pure bipartite state which has some kind
entanglement. Exactly.
It's entanglement. Right.
In classical bipartite pure state, there is no correlation.
Yes. That's true. But
okay, we can discuss that. I think for this is going to be for means everyone is not having part in that discussion. We can have it later, no?
Yes.
Yeah.
Okay, then we can end our meeting here, right?
Yes.
মানিক দা, তুমি কি ফ্রি আছো? দেখো
একদমই নেই।
আমি দেখো, ফ্রি আছো?
একদম না, একদমই নেই এখন।
হ্যাঁ।
ও কিসের জন্য বল?
না, আমি বলছি যে এনভায়রনমেন্টে যদি শুধু আমি হেডও নিই না, তবুও কোরিলেশন তৈরি হবে।
আচ্ছা বল,
রেকর্ডিংটা স্টপ করে
রেকর্ডিংটা স্টপ করে দিই।